Hi, folks. So our last lesson, we went through just what is tidy data, why is it important, and then a brief aside on how to write data out of R in a tidy format, specifically using a .csv file, because we had said that that's sort of like this standard across data science throughout the entire planet. It's a very lightweight file. It does not add a whole lot of extra bloat to the file space or the storage space on a computer. And it's basically every computer on the planet can open a .csv file, whereas not every computer can open these other different data files. Um, this aside, if you will, what we're going to talk about in this video is called the pipe operator. And I have gone back and forth. Part of me thinks that it actually belongs here in the next lesson, the data manipulation with dplyr, but part of it honestly kind of deserves its own thing, really. And we really need to spend some time thinking about this before we get into how to work with tidy data sets in R. So I want to talk about why we call it a pipe operator. And I want you to think about the idea of something called a pipeline. And in many industries, they have something called a production pipeline, or you can think about it as an assembly line, if you will, where there are certain steps in a process. So if you are, and it's an industrial process where lots and lots and lots of operations happen to a lot of units. So it's not like an artist creating one thing at a time, but instead it is a team of people creating hundreds, if not thousands, of the exact copies of this unit. And in this factory, you start with like the raw materials, and it goes through different stages of a factory, and then at the end of the factory, out pops basically a fully formed car, if you will. So if you think about Henry Ford and his invention of the assembly line, where you start with the different pieces of the car, and there's like this track that just moves entirely through the factory, that the different at different stations the workers would work on their part of the car. And so you get to a station where they were only supposed to put the transmission together. And then at that station, they're putting the transmission together, and then they're putting it in the car. And then in the next station, they're only connecting the engine to the transmission through the drivetrain. And so as the car moves down the assembly line, you get more and more and more components added to the car. But what happens further down the assembly line depends on what happened ahead of it in the assembly line. Okay. And it's entirely dependent. So the person down here really can't put the brake pads on the car if the person back here didn't finish the frame of the car. Okay. So you have this idea that there's an assembly line. In computational biology, this is often called the same idea of assembly line is often called like a data analysis pipeline, where we start with the raw data and we go through a whole bunch of steps, and each step kind of a little bit depends on the step before. And at the end, you end up with this data result that can sort of be like consumed or understood by non-computer people. So an example would be that I've got a friend of mine that was working they were working on a particular type of breast cancer. And so they would get a sample from the lab, like a biopsy of the cancer, and it would go to the flow cytometry lab, or it would go to some sort of imaging lab. And then a whole bunch of data would come out of computers in the imaging lab or in the flow cytometry lab or in the flow core, whatever it is. And this data would go onto a hard disk, because it was just tons and tons and tons and tons of data. And then that data would get deposited either virtually or sometimes directly, like it would be walked from one building to the next building, and deposited in the biostatistics and bioinformatics core. And the folks in the biostatistics and bioinformatics core, they plug in this drive or they go online and they download all the data from like a shared resource or whatever. And they have these raw data files. Now, the doctor, the oncologist who ordered the biopsy does not need to see these hundreds of gigabytes of data that happened in the middle. Okay. They don't really need to see the actual values of what happened at each, like if you had DNA methylation or something at each probe in along the genome, or they don't need to see if you've got single cell RNA-seq, the individual gene expression values within the individual cells. That does not help them as a clinician. Okay. What they're really getting at is which drug is going to be the most effective at helping my patient. Okay. But there's this process, there's this pipeline where the cells go into a computer here. The computer spits out data. The data gets moved from one core resource in the cancer center to another core resource in the cancer center. And then at this place, the bioinformaticians and biostatisticians go to work to clean up and wrangle and tease apart and summarize what's happening in this data. And then over some time and over a lot of work, then all of a sudden there's like a 2-page report. And this nice Word document that gets written up by the bioinformatics staff that gets sent back to the clinician that ordered the samples, and it says, we believe that this drug and this other drug, if used in combination, will be the most effective to treat this particular type of cancer. That's what the clinician needs. Okay. The clinician does not need all of the stuff in the middle. Now, all the stuff in the middle is incredibly important. It is a pipeline, a reproducible pipeline. And they build these pipelines because we get data like this every single day. Every single day, there's a new patient coming into the cancer center. And so we have this pipeline built out that we just drop the data in here, and weeks later, bing, out pops this report that goes back to the clinician. Now, there's a whole lot of work that happens in the middle. Believe me, it's not just a bing, but as far as the clinician is concerned, that's kind of all they see. They just know that, like in a week or two, I'm going to get an email from these people in biostats and bioinformatics to say, use this drug. Or yes, this is this particular type of cancer, something along those lines. But the reason that this works is that the folks in the middle in the core system over here, whenever they're analyzing these cells, they have protocols that are already written. And they just say, do this protocol. And then in the middle, the biostats and bioinformatics groups, they have just reams and reams of code already written to analyze the output of this data. And they don't have to start over from scratch. They have a pipeline. Okay. Now, so this is a reproducible pipeline, and it takes a lot of time to develop, but once you've got it developed, you can use it for whatever data comes in at the top is going to give you we're going to get a result at the end of this pipeline. How do we do this in R? Okay, now in a very simple way, we can chain operations together in R using this piece of code right here. Now, we get this for free with the tidyverse. So as soon as you do library tidyverse, you get to use this piece of code right here. There is a keyboard shortcut for it. That keyboard shortcut on Windows is Control-Shift-M. And then on Mac, it's Command-Shift-M. Okay. And what it does is it makes these two lines of code basically identical. It says I can either do a t-test on X where the mean is equal to 1, or I can say take X and perform a t-test on it against the mean equal to 1. Now, you may be looking at this like, what's the point? Why wouldn't I just write this? Why do I need this thing right here? The beauty comes in when you have to do a whole bunch of operations. So up here, instead of having to nest all of this code together, and you have to kind of work from the inside all the way out, you get to follow an order of operations. You get to follow a logical pipeline, and that is take this object, perform this function on it with this with this argument or this option, then take the output from that and perform this function on it with this option, then take the output of that and perform this function on it with this option, then take the output of that, perform this function with this option, then take the output of that and perform this function with this option, and that's the end result. If you had tried to write that with code, you'd end up with this giant, massive nest, like 50 lines long with so many parentheses, and it may work, but if it breaks, good luck figuring out where it broke, because you don't know which function in this giant rat's nest of functions actually went off the rails. Now, if you use it this way, you can run it line by line. You can run this first, like, oh, that works. Then run this. Oh, that works. Then run this. Oh, that errors. That means the error is right here. Okay. It's so much easier than trying to untangle a giant rat's nest. Um, Here's an example. Oh, by the way, go read this University of Cincinnati article of why the pipe operator is nice. But anyway, this code right here, which honestly isn't even that bad, this code we get to rewrite it almost in English, and that is take the baby names object, whatever this is, filter to, now we don't know what this function is doing, but it's way easier to read in English than whatever the heck this is. Okay, we filter to some rows where sex is equal to male and names are equal to Taylor, and then we're selecting whatever the n is, and then we're adding them up. Okay, so I don't know exactly what filter is doing. I don't know exactly what select is doing. We're going to learn these functions in the next lesson, the dplyr lesson. But this whole thing, like, I feel like I've got a much better chance of figuring this out with the help of our friend Google than trying to start here. Okay. There is a comment on non-standard evaluation. If you're going to be developing R packages, I would say don't use the pipe operator the way that, I mean, they're still working on this. Right now, I don't use the pipe operator in my packages. When I write packages, I absolutely use it in all of my other code. But when I'm writing packages for other people to use, I don't use the pipe operator. However, I still 100% use it in all of my day-to-day code, and I will strongly recommend that you do it as well. Once you do it, you're going to start thinking about it, and it's going to make you think through your process logically, and it's going to make you build out pipes and pipelines that other people can come and modify and work with. And realistically, you've already been doing something like this all the way since back in the ggplot lesson. The ggplot lesson, the only difference was the symbol was a plus sign instead of this funny looking thing right here. Still the same idea. Okay. All right. So here is a homework assignment for you. I want you to take this nasty code right here, and I want you to rewrite it with the pipe operator and confirm that you get the same results in both times. Alrighty then, and that'll be all for this. The next thing we're going to get into is lesson 9 on dplyr. So have a good one. Bye-bye.